Hi everyone. Today we are going to cover section 5.1. This is the beginning of our chapter 5 notes. To get started, you'll notice that the title is called Verifying Trigonometric Identities. Okay, so before we get started, I just want to make sure that we got the formula sheet handy. Okay, more importantly, I want us to have it on the side that talks about trigonometric identities, because we will be using formulas or identities off of this page in order to manipulate it on our notes today. Okay, so keep this handy as I will be referencing it many times. So, verifying trig identities, okay? Essentially, for lack of a better word, we're proving something, okay? Now, I don't mean proving something like back in geometry where you had to label the steps and show what you did and how this applies here because of this, okay? That's not what we're doing. We're essentially solving a puzzle, all right? And the reason I say we're solving a puzzle is because we know the end result, we just have to find our way to it. All right, so when I say verify, that's what we're talking about. We're proving the end result. We're proving that it does work, and we are showing the steps as to how. And the way we show those steps is through those trig identities that are on your formula sheet. Okay, so to get started, we have all these guidelines, all right? And honestly, it's a lot of information to take in all at once, but these are just some helpful hints, okay? There's no particular order, so really, truly, the first one's probably the best one to keep in mind. However, not every time do we want to rewrite our terms in terms of sine and cosine, all right? But just as a reminder, what that step talks about is, remember, if we have tangent in our function, just remember the tangent is the same as sine theta over cosine theta. All right, again, these are on your formula sheet, so I just want to reiterate, these are what I mean by rewriting in terms of sine and cosine. So if I gave you tangent, that's an idea to just swap it out for sine over cosine. If we gave you cosecant, just a reminder, that's always 1 over sine theta. And if I gave you secant, that's 1 over cosine theta. Similarly, if I also gave you cotangent, just remembering that it's the reciprocal of tangent, so that means cosine is now on top, followed by sine. All right, and again, these are just to rewrite it. So if I gave you tangent, start thinking sine over cosine. If I gave you cosecant, start thinking 1 over sine, and so forth. Okay, and again, you have that formula sheet if you need it. Another guideline is to factor out the GCF. Okay, remember, greatest common factor. A great reason to factor out the GCF is so that we can cancel some things over our fractions, or we can get things out that will allow me to convert it into another trig function, things like that. So you'll see some examples. And then we have this extra crazy statement here about fractions, okay? It says separate a single term quotient into two terms. So what that means is if you are ever dividing two terms by the same thing, we can split them up into two pieces. All right? Same thing goes for the other direction. I'm going to go on this right one here. If I was subtracting two fractions with the exact same denominator, I can work backwards and put it as one fraction altogether. All right, so I can split it up or I can bring it to 1. Now, I just want to be clear that that does not mean that we can do it the other way. What if my a plus b was down in the denominator? That does not mean I can say c over a plus c over b. Okay, that's not how that works. It can only be a single term down in the denominator, or something that you can still split up. But the numerator is what allows you to split it up, not the denominator. Okay, again, numerator because it had two terms. Then there's combine of fractional expressions using the LCD. Again, that's what I just stated. That's the backwards version. Okay, so we saw that they had the same denominator, or the least common denominator. So I was able to combine those together to make it one fraction. Okay. Another guideline or another opportunity, another option you can use is to multiply the numerator and the denominator by a binomial factor that appears on the other side of the identity. Okay, now this is a lot. What this means is if you know the end result, again, think of it like a puzzle, we know what we're going to want at the end. If I know that I have to somehow end up with a cosine when my original doesn't have cosine whatsoever, that's where this option might be handy. All right. And just like when we multiply fractions before trig and when we did it in algebra or algebra 2 or anything like that, I have to make sure that I multiply both the numerator and the denominator. And the reason that's allowed is because if I multiply anything by cosine theta over another cosine theta, that is still a factor of 1. Okay, it's still the same thing on top of each other. So that allows me to multiply top and bottom. All right. Now this said by a binomial factor, so that just means two terms. Again, you'll start to see the patterns and why that would be useful. It's not a very common guideline that we follow, but it is an option. All right. And again, there's a hint fraction term on the other side. So if we have to introduce some sort of fraction or something like that, then this would be a good opportunity to do so. Last but not least, we have the squared term with 1. Look at the Pythagorean identities, and then of course we can manipulate these identities. Okay, again, these are all on your formula sheet, all 3 of these, exactly as you see them. The reason why this one would be helpful is because each one of these identities has the number 1 with it. So if we want to get 1, if we multiply with 1, we get the same thing, that kind of thing. It will eliminate some things, some trig identities for us just on its own based off of the fact that it can equal 1. And then it also says you can manipulate them. So what that means is it doesn't always have to say sine squared plus cosine squared equals 1. It can also be cosine squared x or theta. Doesn't necessarily mean it has to have theta or x. It can also equal 1 minus sine squared theta. All I did was subtract the sine squared over. That's the manipulation. You're using the same exact function. You're just manipulating it in a way that will benefit you as you're working through these trig identities. Another option, you could keep the sine squared theta or the sine squared x and just subtract your cosine squared x. Okay, so those are your manipulations. I'll go ahead and finish off the rest here. We can have 1 equals secant squared x minus tangent squared x. Or another one could be secant squared x minus 1 equals tangent squared x. And then if I want to manipulate this last one here, I could say 1 equals cosecant squared x minus cotangent squared x. Or I can say cosecant squared x minus 1 equals cotangent squared x. All right. If you want to put these on your own personal formula sheet, that is fine. But remember, the day of your quizzes, tests, final, what have you, these won't be given. So if you need to re-manipulate them, you may do so. It's just a matter of adding that extra time in for that. Okay, again, all on the golden ticket here, formula sheet. Same with the reciprocal identities, just reminding the reciprocal of these things is the other. We're flipping them over, putting them over 1. Also on the golden ticket, all of these are on the golden ticket. Quotient identities, we talked about up above. If you saw tangent, you're going to start thinking sine over cosine. If you saw cotangent, you're going to think cosine over sine. All right. And so let's get started on some problems. All right. So I'm giving you, I'm asking you to verify the identity. Okay. Here are the rules. When we go to verify identities, you may not top sides. Okay, that doesn't mean you can, like, again, we're just verifying. That doesn't mean you can take this cosecant x, move it over to the other side, and keep going. All right, you're only going to work with one side and one side only. You can, however, choose which side you want to work with. And I'll talk about that in our notes and why we would work with one as opposed to the other. All right, so that's rule number 2. You may verify any side. Okay, so that can be the left side or it can be the right side. It doesn't always have to be the left. More often than not, I choose the left, but that's just me. Okay, and again, I'll explain why. And then I have a third rule here that says converting to sine and cosine is always best. All right, and I'm going to go back on the word always just a little bit. So every once in a while, if we see an example, and let's just talk about like one here. What if this didn't say cosecant x? What if it said tangent x? All right. Well, if I used my guideline that said, or my rule that said converting to sine or cosine is always best, well, my end result doesn't have sine or cosine, but I know that tangent is also sine x over cosine x. So just some things to keep in mind. If you introduce a sine or a cosine, just remember you may have to actually go back and get rid of it again just to get back to what you needed at the end. All right, but it's much easier to work with if we have sines and cosines. Just take it from me. All right. So, on question 1, I'm going to solve the left-hand side. And the reason why I'm going to work on the left-hand side is because there's more to work with. All right, and what it's saying is secant x times cotangent x, there's multiplication happening in the middle, has to equal cosecant x. So I have to verify that it is indeed going to get me cosecant x, or it's the same as cosecant x. The trick is I just have to know how. All right. The reason why I wouldn't choose the right-hand side is because I don't have much to work with. All I have is cosecant x. All I know is cosecant x is just 1 over sine x, and that's about it. Okay, it's not going to get me that secant or my cotangent on the other side. So that's why I'm going to use the left. Okay, and I'm going to use one of my rules. So secant x times cotangent x. First thing, I want to convert. Every single time you can, just convert. So secant x is the same as 1 over cosine x. And whatever angle you start with, so in this case our angle was called x, just keep it throughout your work. Sometimes it'll be x, sometimes it will be theta. So I'm going to convert secant x into 1 over cosine x. And then cotangent x is going to get converted into cosine x over sine x. And remember, they were multiplying up above, so I'm going to keep multiplying them down below. I'm not touching anything on the right-hand side. That's what I'm trying to get to. That's my end goal. So I have to make sure at the end of all of this, I get cosecant x. So now looking at my 1 over cosine x times cosine x over sine x, I notice that I have a cosine down below and a cosine up top. So those will get to cancel with one another. So now I have 1 over sine x. All right. Now for some of you, you might see this right now and say, well, 1 over sine x is cosecant x. I'm good to go. I can move on. All right. That's not wrong. However, I do want that added step of letting me know that you do understand that 1 over sine x is still cosecant x, so I'm bringing it back into other terms of sine or cosine, but it's still a version of it. And now I have reached my goal, and I have accomplished my verification. All right, so all that one was needed was to convert to cosines and sines. I was able to eliminate some cosines. which left me with 1 over sine x, which I happen to understand is cosecant x. And there we have it. So let's try question 2 now. I have sine x times tangent x plus cosine x has to equal secant x. All right? And again, when choosing your sides, choose the one that has a little bit more to work with, essentially. All right? So I wouldn't want to choose secant x in this scenario because it doesn't have much to work with. So let's work on the left-hand side. Again, I'm going to convert first thing. That's probably one of the best first steps almost all the time. So I got sine x times sine x over cosine x. Okay, again, if they're attached to one another, we're going to assume multiplication is happening. And then I'm adding cosine x. Okay, so right now I have a denominator in the bottom. All right, in fact, I have a cosine x in the denominator. So what I am going to do, or I guess let's clean this piece up just slightly before I get there. So if I have a sine x times a sine x up top, remember these are technically fractions. When I multiply fractions, I multiply numerators together, denominators together. So the sine x's are now going to become sine squared x over cosine x. And now I get to add just a regular cosine x. And if you want to make it a fraction, we'll put it over 1. All right. Now, here's the tricky part. We have 2 terms, but we need to get down to 1. That's our end goal. All right. So if we have 2 terms, we want to get down to 1. Let's see if we can get those 2 terms together. And the only way to do that is to get the same denominator. So that's where I'm going to look. I'm going to look at my denominators. And I'm going to say, well, my least common denominator between both of those needs to be cosine x. Well, I can't just randomly change one denominator. I need to multiply by a factor of 1. So this second term is going to get multiplied by cosine x over cosine x. This first term does not need a cosine x to get multiplied because it was already there. So here's how it's going to work. First term is going to stay the exact same. And then I'm going to add my second term, which is now cosine squared x over, and my denominator is 1 times cosine x, which is now cosine x. Okay, we're almost there. Can anyone see it? All right. Same denominator now. That was the goal. We wanted to go from 2 terms down to 1. So now that they have the same exact denominators, I can bring those together. So I'm going to just move my work here for you guys. By bringing them together, I'm now going to have a sine squared x plus cosine squared x. And they're all under the same denominator, so it just remains as cosine x. Okay, I understand there were 2 fractions, so we see cosine x twice, so we're going to automatically think, oh, either there needs to be a 2 there or there needs to be a 2 there. Okay, that's not the case. Remember your normal algebraic rules. If I had 1/2 plus 1/4, in order to get the same denominator, I need to get a denominator of 4, which will multiply the numerator by 2. And when I combine them, I got 3 over the same exact denominator of 4. That's exactly what we just did, but with trigonometric functions. All right, so the denominator will still stay as cosine x, and then I got to combine everything else. All right, here's the best part. Take a look at the numerator now. Sine squared x plus cosine squared x. Look at your numerator. Look at your formula sheet. Take a look at sine squared theta plus cosine squared theta. And we see theta, but it's the same idea as if it were to say x. So I can still interpret that the same. And pay attention to what that equals here. It's going to equal 1. Well, that's a trig identity. So whenever I see sine squared theta plus cosine squared theta, I can convert that into a 1. And I'm going to call that a trig identity, just to remind me that is y. So now I have 1 over cosine x. And there we have it. What is 1 over cosine x? Well, it's just in plain old simple secant x. And that's exactly what I was looking to get. All right. So if you guys took a look at my teacher notes, that's a lot simpler, not as many steps, a little bit more organized. If that's what we end up doing at the end of all of this, that is fine. All right. That's our goal, but I got to be able to follow what went where. All right. It's not like we can go from start and say, yep, it equals secant x and call it a winner. All right. No, you have to prove it. You have to verify that, yes, it does work by using your formula sheet, your golden ticket. So let's go ahead and try question 3. Cosine x minus cosine x sine squared x. All right. And sometimes if you get stuck, especially on your homework tonight, if we get stuck, take a step back, all right? Take a look at the end result. The end result wants everything to do with just cosines. So I don't want any sines. Well, in the left-hand side, that's what I have. I have cosines, which is good, but I also have sines. So I have to find a way to get rid of sine squared. All right. But in the meantime, I want to keep a cosine. So this is what I'm going to look at. I'm going to say, well, both those terms on the left-hand side have a cosine in common. So I'm going to factor out that cosine x so I can make sure that it's going to stay with me. So that's my first step, is to factor cosine x. And when I factor that out, again, remembering your steps for factoring back to Algebra 1 and Algebra 2 and even some of Trig, we still have a 1 in the placeholder. When I factor something out, I am dividing it out. So there's still a 1 left there. And then the second term, when I take out the cosine x, I'm left with sine squared x. Okay, we're getting somewhere. Now, we want to get rid of that sine squared x, right? Well, take a look at this entire piece. It happens to also be another trig identity. More importantly, it's the exact same trig identity we had in question 2. It's just a manipulation of it. So I'm going to go back up to this page where I manipulated all my functions. And I'm going to say, hey, that looks a lot like what I have on my paper for question 3, and I know that 1 minus sine squared x has to now get replaced with a cosine squared x. So we go back down to question 3, and I notice that that is cosine squared x, so I'm going to swap that out with cosine squared x. And then just remember, we still have that cosine x from originally. Now we're multiplying. We can distribute that back in, and that will give us cosine cubed. We made it to the end. We can check off. All right. Let's go to question 4 now. Some are easier than others. I promise, I understand. All right. Question 4. So we have a fraction on the left-hand side and then 2 terms on the right-hand side. So this is a scenario where I myself see a fraction and I'm like, I don't really want to mess with a fraction. I can. In fact, it's not bad. And now that I look at it a little bit more, I'm like, okay, a fraction, it's got 2 terms up top and the same denominator down below. So I can actually start off by splitting it. Okay, so again, if you want to try the right-hand side, which it looks like that's what I actually do in my teacher notes, try the right-hand side. You'll get the same thing. You'll notice it's the same idea, I'm actually going to do the left-hand side because I didn't realize it was as easy as I didn't think it was earlier. Okay? So on the left-hand side, we have 1 plus sine theta divided by cosine theta. Well, it's a fraction. It happens to be one of the fractions that I can split into 2. And what I mean by that is I can split it into one term as just 1 over cosine theta, plus my other term of sine theta over cosine theta. Okay, I didn't change a single thing. I just took that fraction and split it into 2 terms. All right. Well, what do you know, guys? I'm already done. 1 over cosine theta. It's the exact same as secant theta. I'll keep it as thetas for you guys. All right. Plus sine over cosine theta, which is now tangent. And there you have it. We're done. All right. Some are easier than others. Some take a little bit of brain power. All right. Question 5. We got 2 separate fractions equaling 2 secant x. All right. Again, I try to steer clear of fractions because that's just my personal preference. However, if I looked at this right-hand side, 2 secant x, not much to work with there. All right, so I do actually have to figure out these 2 fractions on the left. All right, so I got cosine x over 1 plus sine x plus 1 plus sine x over cosine x. Okay, 2 fractions. Right now, I cannot combine these fractions because they are not the same denominators. Okay. The reason I am looking to combine fractions is because I have 2 terms that needs to somehow turn into 1 term. That's why I want to know, or that's how I know that I want to combine them in some way, shape, or form. So, how do I get the same denominator? That's where we're going to look. Find your denominators. In order to get the same denominator, I need to make sure that everything is accounted for. So, I want my new denominator to not only have 1 plus sine x, but I also want it to have a cosine x. Both of them. All right? So I look to my first fraction, and I say, well, my first fraction's denominator has the 1 plus sine x, but it didn't have the cosine x. So in order to introduce a cosine x in the denominator, I need to also introduce it in the numerator. Okay? All I've done is introduce it. Don't forget about the original. So the original is the one here in black, and then the green one is what I introduced. All right. So let's go ahead and get the same denominator on the second term. Same denominator, so I want a 1 plus sine x with a cosine x. In order to get the same denominator, I need to introduce, in this case, I introduced a 1 plus sine x. So I need to do the same thing up above. And then I already had a 1 plus sine x. Okay, go ahead and distribute, see what we get. Distribute, FOIL, whatever we got to do. So we get cosine squared x over, and I'm just going to keep the denominator as is. We'll worry about that if we need to. Plus, and then on the other side I have 1 plus 2 sine x plus sine squared x all over 1 plus sine x cosine x. All right, so now they officially have the same denominator, so now I can bring them together. And again, we're just using addition in the numerator, so if you want, you can rearrange your terms, that's fine. It won't change too many things. Okay. Now, when you're doing your homework, you might be on a step like this and say, well, I don't think I'm going the right direction. Don't worry, okay? Keep going at it. See how we can go from here. The more that we practice, the better it will be, I promise you. All right. Now, I'm stuck. I don't know what I'm doing. What I want you to notice here is we have a cosine squared x. We also have a sine squared x. Well, the one identity that we've been using pretty often is the one that says cosine squared x plus sine squared x has to equal 1. All right? That is the same thing here. Just because they're on opposite ends of that fraction, they're still getting added together. I could rearrange them to put them together. That is fine. So I'm going to use my trig identity to remove those from my numerator and to just make it a 1. So that will now give me 1 plus 1 plus 2 sine x over 1 plus sine x cosine x. All right, again, this new 1 that I got came from my trig identity on my formula sheet. Simplify that just a smidge. 1 plus 1 is going to give me 2. It's the only thing I'm going to clean up right here. So it's kind of getting a little bit smaller. That's good. Now again, if I get stuck, I look to what my end goal is. We know what we need in the end. So we need a 2. Okay, I see a couple 2's in my work. That's good. So that's something I'm going to want to keep. And then I see secant x. Okay, just some things to think about. Secant x includes a cosine. So cosine is going to need to stay in some way, shape, or form. In fact, it's going to want to stay in the denominator. All right, which I happen to have, and it happens to be in the denominator. So what I need to get rid of here is a sine. So I'm going to factor out a 2. In the numerator, I see a 2 in both terms, so I can take that out, leaving me with 1 plus sine x. Down below, same denominator. And now take a look at what we get to cancel. We have a 1 plus sine x up top, a 1 plus sine x down below. So that leaves me with 2 over cosine x. And we know 1 over cosine x, so whenever we see a cosine in the denominator, that gives me a secant. And the 2 is just going to stay in the front. All right, and there we have it. We got it to work. Okay. All right. Question 6. We have a fraction on both sides, which is fine. All right, but what I want to make sure I get across to you guys is we can only do one side. We can't jump back and forth. So that immediately needs to tell you guys that you cannot go and start cross multiplying. All right, I know we see a fraction on both sides. I know we're used to it, but because we're verifying, we have to not touch one side and only touch the other. Okay, so on this one, again, I'm going to go a little bit differently from my teacher notes. My teacher notes uses difference of squares. It's not ideal. I don't really like to use difference of squares, but we can. I'm actually going to use the right-hand side. I'm going to solve this one. And the reason I'm going to try this one right now is because my denominator is only one term. And when it's one term, I can split it off into 2. The other version, I would have had to multiply by a binomial factor and yada yada yada, and it's a little bit of work, not gonna lie. All right, so what I'm gonna do is I'm gonna work with the left or the right hand side, and I'm gonna start by splitting it off. 1 over sine x minus cosine x over sine x. All right, and I'm kind of doing this one with you guys because I have yet to try it this way. Okay, now take a look at what we have and what we're going to need. Okay, we're going to need a sign in the numerator, and then we're going to need to have a cosine in the denominator. How is this going to work is the question. Okay. Well, let's start off by introducing some sort of sign in the numerator. Okay, if that's what I want, let's introduce it. All right. And I think I just found the way. All right. So in order to introduce a sign into the numerator, we can multiply it by sine x, but we can't just multiply it by sine x. We have to multiply it by sine x over sine x. Okay, again, think of that factor of 1. If you do it to the top, we got to do it to the bottom. And I'm going to make sure that I do it to both terms here. All right. I'm going to actually come to find out that I didn't need to separate these fractions, but it's okay. Sometimes in our work, we sometimes do more work than we needed to, but that's okay. So that gives me sine x minus sine x cosine x over sine squared x. And the reason why I brought these back together as one term is because my denominator is now sine squared x. That should be a hint. When we see those squared, sometimes they're very, very helpful. And that, my friends, is a trig identity. So let's use it. Sine squared x is going to be the same as 1 minus cosine x in the denominator. And I'm going to factor out that sine x up in the numerator, leaving me with this. So it looks like difference of squares is actually needed regardless of which method we use. And the reason I say that is because now we have a sine x in the numerator, so we're good there. But I need to somehow get a 1 plus cosine x in the denominator. All right? That's where difference of squares comes in. So, remember this. Back when I asked you to factor difference of squares, if it was x squared minus 4, you would tell me that the two factors were an x plus 2 and an x minus 2. Same thing is going to get applied here. It's just that our squared term, or I guess they're both squareds because 1 squared is still 1, but then the second term is going to be a cosine that gets squared. So when I perform the difference of squares here, it's going to turn into the same numerator, and then the denominator is going to be a 1 plus cosine x version, followed by 1 minus cosine x. And whenever you're questioning any of this, guys, just go ahead. You know the math, you know the skills to double distribute and FOIL back. And if we did that, we would get the same denominator that we had. Okay, so you can always go back and check. But the beauty of this is now I see that I had a difference of squares, which will allow me to eliminate that 1 minus cosine x, leaving me with sine x over 1 plus cosine x. And we did it. All right, so I'm going to leave a few of these for you guys to practice with. Okay, my teacher notes are available, so you can find them on Teams and see how it's going from there. A lot of it is just practicing with those trig identities. All right, question 9, if you look at question 9, has 1 plus cotangent squared x. That's a simple trig identity. Find your formula sheet, swap it out, and it's about a 2-step problem. Okay, question 10. We'll make question 10 a challenge for you guys. We got to work with the left-hand side. I need you to first double distribute or FOIL, whichever way you know it as. And when you do that, some things will cancel or eliminate each other. And then you'll be left with a trig identity. So yes, it looks messy, but honestly, it's a 2-step problem. once you get foiling. Okay, so the rest of these are about 2 to 4 steps depending on which method you go. All right, but we can try them. Again, my teacher notes are posted if you want to get started and just look at those. If you want to try it on your own and then check, see if you're on the right path, go ahead and do so. I highly recommend it, but keep that golden ticket handy.